Funding at this point, so maybe let's go ahead and get started. It's really good to see you guys. I'm glad to see that you're all safe and sound and back from Thanksgiving. I know I needed that time to catch up on a few things and to get a little bit of rest. I hope you guys got the same. So this is the last week of lectures and content before we go into final exam week next week. The semester has not gone the way that I had planned. We didn't cover as much material as I would have liked. I was not as on top of giving you guys homework assignments and getting grades back. Definitely not optimum, but I think it's time that I have to face facts about where we stand and make sure that we're on the same page for the end of the semester. So first things first, next week is final exam week. Our class's scheduled final exam period is on Thursday from 8 to 10 a.m. That is not especially relevant for us because I'm giving the final exam as a take-home exam that can be done over the course of the entire week. So I'm still putting it together, but my plan is to give it to you guys this Friday and give you a week to do it so that you can give it back to me the following Friday. I had really hoped to be able to squeeze in one more short homework assignment on the stuff that we've been covering right before Thanksgiving and this week, but I have to face the facts that there's just not time to put all of that together, and given the number of people who still need to submit homework 3 and homework 4, it seemed like that would be a bad idea for everybody. So I have decided against writing another homework assignment. I will just leave it at the 4 homework assignments that we have. That means that the final exam will cover the course material that we've covered already that you've had homeworks on up through homework 4, as well as the little bit of new stuff that we've covered since then, the harmonic oscillator and rotations. The plan for this week is today we will finish up rotations in 2 and 3 dimensions, and I think that will put us in a good position on Thursday to end the class by talking about spin and the rotations generated by spin, which I think is a nice summary and capstone of the symmetry transformations we've been talking about all semester. So if the final exam is being done as a take-home, then we have this block of time next week. I will be available during that time, so please feel free to come to me. Treat it like office hours if you have questions, problems with the homework, problems with the final exam, anything that you need help on, I will be around. Additionally, my plan was, in the absence of any problems or questions from you guys, I wanted to look up some examples of previous problems that have been given on NMSU's qualifying exam and or comprehensive exam related to quantum mechanics. And I can't promise that everything that I will do will be 100% perfect in terms of, getting you a full score on those kind of problems. But I wanted to work some things out in class during that time to show you how to apply some of the things that we've been doing in class to the kind of problems that are there on the qualifying and the comprehensive exams. So this was my plan as far as final exam week next week. Any questions or comments on that? Okay. The other thing, I think we've mostly touched on all of this already. So student evaluations are things that I thought maybe would happen automatically on Canvas, or I could click 2 buttons and I could add the student evaluations to Canvas. Seems like it's not that easy and I need to call someone to help me walk me through the process. But I'm going to get the student evaluations for this course up on Canvas one way or another, hopefully today, so that you have the rest of the week to log on and give some feedback about how the semester has gone. This has been a really messed up semester, I'm sure more so for you than for me, but I would really appreciate your feedback about how the class has gone, whether the lecture material that I've tried to pick out has been helpful or a distraction. Any feedback that you have for me would be welcome. So I'm working on getting this up on Canvas hopefully today. I mentioned some people who still have outstanding homeworks 3 and 4 that have not been submitted yet. I haven't given any late penalties. I don't intend to give any late penalties, but please get them in. Just make sure that you don't have any zeros in the gradebook. I will grade these things and accept them up until the very last minute. Similarly, for homeworks that you've already submitted, for points that you've lost, you have the opportunity to submit corrections, and I will grade all of those up until the very last minute. So you can recover up to 50% of the points that you lost on the homework assignment back. I think that's everything on my radar right now as far as logistical issues, things that I owe you. Do you have any other questions or concerns for me about the state of the class?
Just a comment on the evaluations. At least on my end, the course evaluations, they show up on Canvas for me. for this course.
Oh, they are there on campus already for you?
Yes. Well, they show up for mine. I opened up right now, and I have.
Oh, okay. Maybe it's not as bad as I thought. Then I have to do some homework on that. But okay, fantastic. So if you can do the evaluations for the course, I would really appreciate it.
Sounds good.
Thank you. Any other questions or concerns at this point? Okay, thank you very much. I'm really glad that the audio seems to be working now. Hopefully this means that we will have a nice recording of the entire class from the Blackboard. I wish I had been able to get all of these details ironed out earlier in the semester for you. I'm sorry about how that's going. Okay, if there's nothing else, then let's dive into physics for the day. As always, please give me a holler if you can't see something or if it's not clear on the board or camera's not focused or whatever. All right, so last time we were discussing angular momentum and rotations in 2 dimensions. The classical transformation that we were trying to implement was one that generates a rotated position vector r prime as a rotation matrix r of theta multiplying the untransformed position vector r. Likewise, a rotation also rotates the momentum. The same rotation matrix r of theta multiplies the position vector p and gives you p prime and r prime, where that rotation matrix r of theta was just the 2x2 matrix cosine theta, negative sine theta, cosine theta. So what we showed last time was that the classical version of the transformation is obtained for any observable omega after rotation by an angle theta. This is obtained by exponentiating the Poisson bracket with the generator of rotations in 2 dimensions, which is the z component of angular momentum. The parameter of the transformation is the angle theta, and this acts on the observable without the angle rotation. And this operation of performing various derivatives over and over again, as in the exponentiated Poisson bracket, transforms the observable without a rotation into one with a rotation. And we said that this algebraic formulation tells you under canonical quantization how to get the quantum transformation of an operator, omega hat of theta, is obtained by replacing this thing with the Poisson bracket. Sorry, the Poisson bracket gets replaced with the commutator. E to the minus I over h bar commutator with the angular momentum operator. And when this is a commutator, it can be written more simply as e to the plus I over h bar Lz theta omega naught e to the minus I over h bar Lz theta. And we said, just like the Heisenberg picture of time dependence, you have some freedom to decide how much you want to consider the rotation or the transformation of the operator versus how much you want to consider the transformation of the states. And so the operator that generates rotations on the states is this unitary operator, u of theta. And so then the one on this side is u dagger of theta. And so with this setup, you can either think about it as either the operator is transforming or the state is rotating. And then in that case, a rotated state psi of theta is just obtained by letting that unitary operator u of theta act on the initial state psi naught. And so this is just obtained by e to the minus I over h bar Lz theta acting on the original state. After we discussed how to implement rotational transformations, we talked about the eigenvalues and the eigenstates associated with that angular momentum operator. So we found that the quantum number associated with angular momentum is an integer value called the magnetic quantum number m. This is just the z component of angular momentum in units of h bar. And the eigenfunctions, or the wave functions associated with this, we can call them phi m of theta. This is just a notation for that eigenstate m in a position basis in polar coordinates. This was just given by 1 over square root of 2 pi e to the im theta. The quantization of angular momentum came from demanding that the wave function be continuous after a rotation by 2 pi. Okay, so that's the recap of what we discussed last time before we took a nice break for Turkey Day. Any questions on this recap before we now extend this to 3 dimensions? Okay. Oh, actually, before we go all the way to 3 dimensions, a few other comments. So, a nice summary of the rotation properties. It's useful to classify operators based on how they transform under rotations. And so we can classify operators as a scalar, meaning something that's invariant under a rotation. So that means if I have an operator omega and I transform it by a rotation, if omega is a scalar operator, then it is invariant under the rotation. So it just gives itself back. And it's easy to see if you multiply this operator u to the right-hand side and subtract. This means that omega commutes with the rotation operator. And if it commutes with the rotation operator, it commutes with the generator. So a scalar operator is just one that's invariant under rotations. A vector operator is not invariant, but it gets rotated among its components like a vector should. So the notation here gets a little bit weird. I would write this as v vector and a hat on top of it because it's an operator. This just means that there are components of that vector. Those components are operators. And they multiply some basis vectors. Normally I would put a hat on these because they're unit vectors, but I don't want to use hat because I'm using hats for operators. So I'm just going to call them EI as vectors. So this operator is a vector in the usual way. And if it's a vector, then that means it should rotate like a vector. So that means when I take the component vi and I transform it with a rotation, I shouldn't get back the same vi. The vector actually gets rotated. And it gets rotated like that 2x2 matrix. So this is R of theta, that 2 by 2 matrix, I prime component, dI prime. So this is kind of a cool equation. On the left-hand side, this is the quantum representation of the transformation. And on the right side, this is literally saying that this is that 2 by 2 matrix, cosine theta, negative sine theta, cosine theta, multiplying the vector v. So this is the classical version of that rotation. And hopefully, if you understand where this comes from, the symmetry arguments that generate the same transformations, then you see that these are the same symmetry, the same rotation, just in two different representations. This is the rotation generated by commutators in quantum land. This is the rotation generated by Poisson brackets in classical. And the connection is the operator gets rotated among its components just like a classical vector should under this quantum transformation. And we're not going to need this next step among ourselves probably until next semester, but it's worth mentioning that you can generalize this transformation to tensor operators. So if I have, for instance, a 2 by 2 matrix, then each index of that tensor gets rotated just like a vector. That's the definition of what a tensor is. It rotates like a vector with many components, many indices. So the version of this is that the quantum transformation, let me just write u dagger of theta, u of theta, and it rotates both indices, I and j. So same statement, the quantum action on this operator, if it rotates like a tensor, means that each of those indices gets rotated among the corresponding. Okay, there were a few loose ends that I gestured at the end of last class, but didn't have time to really go through carefully, and I want to repeat that now. So when we have rotationally invariant Hamiltonians, that rotational invariance just means essentially that H is a scalar. And as we already discussed, this implies that that Hamiltonian commutes with the generator of the symmetry transformation, which is the Z component of angular momentum. So this means that the Hamiltonian and the Z component of angular momentum are simultaneously diagonalizable. So I can have H acting on a set of shared eigenstates with quantum numbers E and M. The Hamiltonian H returns the eigenvalue P. The Z component of angular momentum returns MH bar. And since these guys commute, that means that we know some of the information about the wave function. That my eigenfunction, or the eigenstate psi in polar coordinates, which depends on r and theta, this wave function is just a shorthand for what I mean when I say I take that eigenstate with quantum numbers E and M, and I project it onto a position vector in polar coordinates. So this is just another way of writing the position bra r. And we don't know anything about the radial dependence of this. It's some unknown function, capital R, but we do know that it must have the angular dependence associated with the eigenfunctions of Lz. Since we know for any Hamiltonian that commutes with Lz, we know what the angular properties of Lz are. So this wave function must be written as some unknown dependence on R times 1 over root 2 pi e to the I m theta. And so this lets us simplify a two-dimensional Hamiltonian problem that possesses rotational invariance down to a one-dimensional radial problem. So the time-independent Schrodinger equation written in coordinate space is Hamiltonian operator on my eigenstate written in position space, meaning I project it onto a position eigenstate. As a differential operator, this is minus h bar squared over 2m, where m is the mass. Since I'm already using m for the quantum number, I don't want to reuse it. So I will call the mass mu. So this is h bar squared over 2 mu, the Laplacian in two dimensions, acting on psi, plus v of r is a function only of the radial coordinate if it's going to be rotationally invariant. Psi of r equals e psi of r. If you plug in what the Laplacian is in polar coordinates, that Laplacian is just the combination 1 over r ddr times r ddr of psi. That's the radial part plus 1 over r squared d squared theta squared. And so the advantage is if I know the form, especially the angular dependence of the wave function coming from the fact that they are eigenstates of Lz, then I know how to take the beta derivatives, even if I don't know anything about that radial function r. So when I plug in this form, I get a differential equation for r, and I end up with minus h bar squared over 2 mu, 1 over r ddr r dr plus the quantum number m squared h bar squared over 2 mu r squared plus v of r times the radial wave function r equals e times the radial wave function. So this is the radial Schrodinger equation. And it has nice physics that you can pick apart. This is the radial momentum. So this is like p radial squared over 2 mu. Note that the radial momentum is this weird combination of derivatives in polar coordinates. It's not just ddr squared. This piece is associated with the angular momentum. So this is essentially L squared over 2 mu r squared. In classical mechanics, this is referred to as the centrifugal barrier term. This is essentially the kinetic energy that must be possessed to move with that amount of angular momentum at that radius. And for fixed value of the quantum number m, fixed value of that angular momentum, that effectively adds to your potential like it's a repulsive potential energy. So with this, now you have a one-dimensional equation that you can solve for a given potential V of r. You can solve for the radial Schrodinger equation. So just by way of example, if we take the free particle in 2 dimensions, v equals 0, then the radial equation that we have is minus h bar squared over 2 mu. If I expand that combination of derivatives, I get the combination d squared r dr squared plus 1 over r d capital R d little r. I can combine the centrifugal barrier with the actual energy, m squared h bar squared 2 mu r squared minus e r equals 0. So I can clean this expression up a little bit. Let me move the dimensionful constants away from these derivatives. I'll multiply through in the equation. If I do that, then I can write this differential equation as r double prime plus 1 over r single prime plus 2 mu e over h bar squared r squared minus m squared over r squared and this is more conventionally written if I multiply through like I was trying to do a moment ago, multiply through by r squared r double prime plus r single prime plus 2 mu e over h bar squared r squared minus the quantum number m squared r equals 0. And I won't belabor all of this by going through the series solution, but this equation is a very famous one. This is Bessel's equation. And the solution to Bessel's equation are the Bessel functions of r scales like the Bessel function Jm, where m is the magnetic quantum number, of kr, where k is effectively a radial wave number. That is square root 2me over h bar squared. So this is the solution to the free particle problem with 2D rotational symmetry. You could write it down as a differential equation in Cartesian coordinates and write it as a product of plane waves in x, plane waves in y. There, the rotational symmetry would not be manifest. If you make the rotational symmetry manifest, then the natural solution looks like rotational plane waves, e to the I m theta in the angular variable, angular excitations, and then a radial plane wave solution, where the radial plane waves type solutions are the Bessel functions. And again, that wave number is exactly what it would have been. Sorry, I think this m is supposed to be the mass, so I should call it mu. Exactly the same kind of wave number that we would have had in one. And I should also mention another simple classical example that you can do, or canonical example that you can do, is the harmonic oscillator in 2 dimensions. That's, again, very similar to the case of the harmonic oscillator in 1 dimension, converted to a radial problem just like this. The 2D isotropic harmonic oscillator is one that I'm considering to put on the fly. So any questions about how the conversion to a radial equation works for something with rotational symmetry? Okay. So for those keeping score, the other 2D rotational problem that's very straightforward and a nice application, that I'm also considering for the final is maybe instead the problem of Landau levels. That's the cyclotron motion of a charged particle in an external magnetic field. Okay, with those comments out of the way, now let's start talking about rotations in 3 dimensions. So the difference between rotations in 2 dimensions and in 3 dimensions is that in 2D there's always one axis that you're rotating around. It's always the z-axis. And because of that, all of the rotations commute with each other. So the symmetry group was SO2, the rotation group in 2 dimensions, which is a commutative abelian group. That is no longer the case in 3 dimensions. Because now there are 3 independent axes of rotation. And those rotation about different axes do not commute. So each individual rotation works exactly the way that we expect it to. So we have rotations about x, and y, and z. So if I call a general transformation, say, omega after being rotated by theta x along the x-axis, theta y along the y-axis, theta z along the z-axis, I know how to write down what those transformations look like for one axis at a time. Omega of theta x, leaving the others alone, should be e to the Poisson bracket, fill in the blank with Lx, the generator of rotations about the x-axis. The parameter is theta x. And same for the other ones. 0, theta y, 0. The z is the case we just discussed. 0, 0, theta z. E to the Poisson bracket with Lz, theta z, omega naught. The tricky part comes from putting these together, since the ingredients do not commute. So we want to figure out what is this transformed omega, even classically, for arbitrary rotations around x, y, and z. We know that this thing should be expressible as some kind of generator. It should be e to the Poisson bracket of something with a generator somehow made out of the angular momentum. And there should be some thetas involved here. So essentially the exercise that we're doing now is trying to identify what is the vector structure that goes up here. So we can see that the rotations don't commute. If I try to just string together these 3 transformations, I can write it down. So I could say omega of theta x, theta y, theta z. If I just nest them one after another, I could have e to the Poisson bracket with Lx, theta x, but then that acts on e to the Poisson bracket of whatever comes next with Ly, theta y, but then that also acts on e to the Poisson bracket of whatever comes next with Lz, theta z. So clearly this is a big mess if you try to build up the rotations one axis at a time. So the way out is to say I can identify that generator just by looking at the infinitesimal transformations. So we're going to take those thetas to be epsilons and consider them to be small. And if I can match that expression on the right-hand side to find out what that generator structure is, then I immediately know the answer. So if I take thetas to be epsilons. So now let's make this epsilon x, epsilon y, and epsilon z, and I expand to lowest order. So let's build it up piece by piece. Maybe I'll start over here. So this expression, e to the fill in the blank lz epsilon z, this just becomes 1 plus Poisson bracket, fill in the blank, LZ, epsilon z, acting on omega naught. So this is just omega naught plus Poisson bracket of omega naught with LZ times epsilon z, up to second order corrections in epsilon. So after I've done an infinitesimal rotation about the z-axis, now I do an infinitesimal rotation about the y-axis. So the second step looks like okay, so in the same way I expand this to lowest order, I know how it's going to act on omega naught. This is going to give me omega naught plus Poisson bracket omega naught Ly epsilon y. I also have a term where the Poisson bracket acts on that Poisson bracket, but that term is going to be second order small in epsilon. It's already got one epsilon here, and the term where the epsilon contributes from up here would be epsilon squared. Since that's an epsilon squared contribution, we ignore it. That is 0 at this level of accuracy. So this piece just comes along for the ride. And the same thing is going to happen when I do my final infinitesimal rotation about x. This will rotate omega naught. But anything where it would touch the other pieces that already have an epsilon in it is higher order. So when I plug it all in, I get the infinitesimal transformation, epsilon x, epsilon y, epsilon z, is omega naught plus Poisson bracket omega naught Lx, epsilon x, plus Poisson bracket omega naught Ly, epsilon y, plus Poisson bracket omega naught Lz, epsilon z, plus corrections that are epsilon squared. And now I see what the vector structure is. I just have Lx, epsilon x, Ly, epsilon y, Lz, epsilon z. That looks like a very convenient dot product. So what we've shown is that omega of epsilon vector, a three-dimensional vector made up of epsilon x, y, and z, is equal to omega naught plus Poisson bracket of omega naught with the vector epsilon, dot product with the vector L, dot product with the vector epsilon. So this is kind of a neat result. The large rotations by a large angle theta definitely do not commute. You have a big messy structure. But the infinitesimal rotations, if it's so small that I can ignore that cross-term, crosstalk, those infinitesimal rotations do commute. And having expanded this out, and we get the first non-trivial piece for any direction of rotation, we can identify this part as the generator of rotations in 3 dimensions. So we know how to build up now all 3 ingredients in terms of the vector L. So this uniquely tells us what the rotation is for any theta, a large angle theta about x, y, and or z. This is exponentiation of the Poisson bracket with the vector angular momentum L, dot product with the vector epsilon. So it's a sum of three different Poisson brackets, x, y, and z, up in the exponent, acting on the untransformed observer. And this uniquely tells us what the quantum version of that rotation is. I turn the Poisson bracket into a commutator with IH bars, and I put hats on it. Omega hat of theta vector is e to the minus I over h bar, commutator with L vector operator, dot product with the parameter theta, which is now a vector, x, y, and z. So we now identify that generator structure. And likewise, in the same way, we can split up when this is a quantum transformation into unitary operator on the left, unitary operator on the right. So this is e to the plus I over h bar, L vector operator dot theta vector. Space here. Omega naught, e to the minus I over h bar, L vector operator dot theta. And again, these are the unitary transformations that transform the states. This is a rotation by the angle theta vector, and this is just u dagger of that state theta. And so the rotation on the states, a state which has been rotated by an angle theta, is obtained by that unitary transformation acting on the untransformed state, which is e to the minus I over h bar, L vector operator dot theta. Okay, so the algebra of symmetry transformations is always the same no matter how complicated it gets. The key is always identifying the generator. And the generator is the conserved quantity, and it always comes from the infinitesimal version of the transformation. Okay, I think it's good at this point to do a sanity check. We derived this very abstract-looking thing in terms of Poisson brackets with a vector up in the exponent. Does it work the way it should? Before I believe that we've correctly generated the quantum transformation, let's double check that it works for the classical transformation. So supposedly, if I transform R to a rotated version R prime, that R prime should be obtained by e to the fill-in-the-blank Poisson bracket of L dot theta with the untransformed vector R. So another way to write this is to say that the ith component of R prime is obtained by e to the Poisson bracket, let's say, Ri, L dot theta. So let's consider an infinitesimal rotation about any axis. And let's just look at the rotation. I guess this guy depends on the angle theta. So let's just look at one component for clarity. So the rotation of x. So x prime of theta under a rotation should be obtained by x plus the Poisson bracket of x with L dot epsilon plus higher orders. Okay, so what is this Poisson bracket? This is x plus, I have separate components, x, Lx, epsilon x, x, Ly, epsilon y, x, Lz, epsilon z. So continuing x prime of the rotation epsilon as a vector in any direction is the original x plus the Poisson bracket of x with x component of angular momentum, if I write it out explicitly, is y pz minus c py epsilon x plus x with the y component of angular momentum, which is c px minus, yeah, that's right, x pz. This is the y component of angular plus x with the z component of angular momentum, which is x py minus y px, plus corrections of order epsilon squared. Okay, we have a whole bunch of things, a whole bunch of terms in the Poisson brackets, but these are all canonical variables. So I know the Poisson bracket of x with x, y, or z is always 0. I know the wrong combination of x with pz or py is also always 0. So for instance, that first Poisson bracket, x with y gives me 0, x with pz gives me 0, x with z gives me 0, x with py gives me 0. This entire thing is 0. For the other two Poisson brackets, there's only one or two non-trivial combinations. X and z doesn't give me anything. X and px is going to give me something. X and x is not going to give me anything. X and pz is not going to give me anything. So there's only one term out of this Poisson bracket that's going to give me something non-zero. In the same way for this last one, it's only x and px that's going to give me something non-zero. Yes, very good. So if I open up the brackets using the rules of the Poisson algebra, this is x plus c, Poisson bracket of x with px, epsilon y, minus y, Poisson bracket of x with px. And these Poisson brackets are just one, since these are their own correct canonical pairs. So I just get x plus z epsilon y minus y epsilon z, which I dropped, plus order epsilon squared. And this combination z epsilon y minus y epsilon z looks like a cross product. So this is x plus the cross product of r cross epsilon, that x component. So if I do the same thing for the other components, y and z, then this statement just generalizes to the vector statement. So the transformation r prime under any infinitesimal rotation epsilon is the original r I started with plus epsilon cross r. Is that the right answer? Yes. I'll try to draw it, but please forgive me, I am definitely not an artist. So suppose that my axis of rotation is this vertical axis here, and this is not necessarily x, y, z, but this is the axis of rotation and the plane orthogonal to it. So my epsilon vector points this way. If I start off with some vector originally R with some projection out here along the axis of epsilon and orthogonal to the axis of epsilon. Then under this rotation, it rotates about the axis epsilon by an amount magnitude of epsilon. So that rotates this vector in this 2D plane. And I get another vector here. This is my r prime of epsilon. So the vector has rotated in that 2D plane perpendicular to the axis of rotation by an amount epsilon. The projection, which is parallel to epsilon, is unchanged. So I see the amount of change parallel to epsilon is 0. This cross product only changes something perpendicular to epsilon. And that cross product gives me that cosine theta, minus sine theta, cosine theta rotation in the 2D plane. So this is in fact the correct formula for the rotation in 2 dimensions, in 3 dimensions, classic. And all of this is completely contained within the algebra of Poisson brackets with that generator vector L. And so we can have confidence that we are extending that correctly to quantum mechanics by turning that into a commutator. Okay, so all of the information about how these rotations work is contained in the algebra of the generators, the commutators with Lx, Ly, Lz. So one thing that we quickly find is that if I take the commutator of Lx with one of the other components, they have a nice cyclic commutation algebra between them. So if I plug these things in, this is Lx is ypz minus zpy. Ly is zpx minus xpz. Again, most of these combinations are 0 because all of the mismatch variables commute with each other. So y and z commute, y and x commute, y and px commute, y and pz commute. The only thing that's not going to commute are the canonically conjugate pairs. So I have pz and z, that's going to give me something. pz and the other stuff is not going to give me anything. And in this term, py has nothing to couple to, z can couple to pz. So this one can combine with that. So again, of all of these possible terms, only 2 of them are non-zero. So when I take this combination in blue, that factor of y pops out in front. The order is important. Commutator of pz with z. That px pops out the back. And then for this term, I have minus, minus, so I get a plus. Now py pops out the back. I have z with pz, and x is in front. So these are the canonical conjugate pairs. Z with pz is IH bar. This one is the same thing, but in the other order. So this is minus IH bar. So I get, if I reorder the terms, this is IH bar x py minus y px. And this combination is nothing more than LZ. And this relation, if you try it for other components, is cyclic. So one summarizes this by saying we had commutator of Lx and Ly gave me IH bar Lz. Ly with Lz gives me IH bar Lx. And Lc Lx is IH bar Ly. So I've got XYZ, XYZ, XYZ. And all of these are compactly summarized by saying the commutator of any two, Li, Lj, is this. Sum over K, the Levi-Civita symbol, epsilon ijk Lk. So I want to pause and make a point about this algebra. This one statement is incredibly compact, but it contains within it all of the behavior of what a rotation is. Right? So this algebra specifies how angular momentum works. This specifies how rotations are generated. So the point is that anything with this algebra is a generator of some kind of rotations. And that means anything with an algebra like this acts like an angular momentum. In terms of conservation laws and everything else, even if it's not R cross P. So the thing that I'm trying to allude to here is, of course, spin. And with whatever time remains to me on Thursday, I want to talk about how this picture generalizes to include spin. These generators rotate the entire wave function. They rotate a function of an infinite number of degrees of freedom. It's a wave function at every point x, y, and z in all of space. The thing that one can add to this is a rotation among a finite number of degrees of freedom. If you've got a new quantum number that comes in exactly 2 different states, or exactly 3 different states, or n different states, any finite dimensional representation, rotation among those n components will have generators that obey a symmetry exactly like this. And those generators will be called spin. They will generate rotations among the internal degrees of freedom. And they will act like a new source of angular momentum that will combine with the orbital angular momentum described here. Okay, how much time do I got? 15 minutes. But just like at the beginning of class, I wrote down the summary of rotations of scalar, vector, and tensor operators in 2 dimensions. It's the same story now with rotations in 3 dimensions. So a scalar operator is one that is invariant under the rotation in 3 dimensions. A vector operator is one that gets rotated among its 3 by 3 components. Vi. And on the right now, I've got a sum over I prime, a rotation matrix in 3 dimensions, R of theta, I prime, times VI prime. This rotation matrix, the classical one, is not the sine theta, cosine theta. That was the 2 by 2 matrix. This is the 3 by 3 version of it. And so this is the one that you look up on Wikipedia and has all the formulas involving Euler angles. I don't think there's any benefit to me writing it out here. And in the same way, you can write down the transformation for a tensor operator. Anything with more indices, each index rotates the same way. Dagger of theta, Tij, or however many indices you have. U of theta is sum over I prime, J prime, however many indices. R, I prime, I prime. R, J, J prime. T, I prime, J prime. So your ideas of scalar and vector work the same way in quantum mechanics as operators as they did classically, as long as you use the right transformation. And in particular, one very important scalar is the total angular momentum. Just write L squared the vector L would rotate like a vector, but L squared rotates like a scalar. And that means it should be invariant under rotations. So this implies that the commutation between L squared and any one of the components, Li, rotation about any axis, must be equal to 0. I have in the notes the proof that this is true. I don't want to spend the time going through the algebra to show that now. But it should be clear that this is a scalar in the usual sense, so it commutes with a rotation center. And therefore it commutes with the generators of rotations. So what this means is that I can find simultaneous eigenstates of the scalar L squared and any of the components of angular momentum that I want. So the different components of angular momentum don't commute with each other. They cannot be simultaneously diagonalized amongst themselves. But any one of them can be simultaneously diagonalized with L squared. So conventionally, we take that to be Lz. So we will look for simultaneous eigenstates of L squared with quantum numbers, whatever the angular momentum is, L squared. We know what the quantum number m is associated with Lz. And so we want to identify what is the relationship of these operators to each other and what possible values of L squared can there be. And as usual, the answer is completely contained within the algebra of the operators themselves. So it's useful to unpack what L squared is. We said that it's equal to Lx squared plus Ly squared and Lz squared. These guys have an interesting algebraic relation to each other. LZ commutes with the whole schmear, and LZ commutes with LZ squared, obviously. But LZ does not separately commute with LX and LY. So there's an algebraic relationship between them contained in the non-commutation with LX and the non-commutation with LY, but still the commutation with the squares. So what I'm saying is LZ commutes with L squared and LZ squared, obviously. Which means LZ commutes with the combination LX squared plus LY squared. And so the situation here starts to look similar to the case that we encountered before with the harmonic oscillator. That we have some combined operator that's made up of perfect squares. And we'd like to unpack that algebra of the perfect square in terms of each individual root of it. So the trick that we use to diagonalize the harmonic oscillator at the operator level will work for us again. We're going to take that combination Lx squared plus Ly squared and factor it. If these were classical, just scalar numbers, Lx squared plus Ly squared, then I could write this as Lx plus I Ly, Lx minus I Ly. And then it would look like a difference of squares, and that would give me Lx squared plus Ly squared. Since they're operators that do not commute, that almost works, but the non-commutation shows up as an extra term. And that extra term is what's going to give us the solution for these eigenvalues. So if I intend to factor these things out, the natural roots that I would define, I'll call L plus or L minus, which are Lx plus or minus I Ly. And the whole point of doing that is that now the combination which multiplies the two of them, let's say L plus times L minus, when I multiply this out, I get Lx squared. From the other perfect square term, I get plus Ly squared. But I also get a non-trivial cross term. I get minus I Lx Ly plus I Ly Lx. This guy is a commutator. I know what the commutator of Lx and Ly is. It's I h bar Lc. And this starts to look really suspiciously like the harmonic oscillator. That we have a combination of these operators that gives you the perfect square you wanted, plus something extra. It appears to raise the value of Lz by 1 unit of angular momentum. So let's wrap it up. So if I take this object and now I get the commutator of L plus and L minus with LZ, I will spare you the algebra and just give you the punchline. I have commutator of LZ with L plus or minus gives me plus or minus H bar L plus or minus. That's essentially the version of what we've written here. Yeah, let's stick with this. And that looks awfully familiar to the creation and annihilation operators that we saw for the harmonic oscillator. Recall that we have the commutation relations A dagger A with A dagger gave me plus A dagger. This was the raising operator, or the creation operator A dagger. And we had A dagger A with A gave us minus A, lowering up. So you see that this algebra operator with L plus gives you the same thing back with plus 1 unit. Operator with L minus gives you the same thing back with minus 1 unit. So it looks like L plus and L minus act as raising and lowering operators to create a ladder of allowed values, a ladder of quantum states of angular momentum, exactly the same way that we had for the harmonic oscillator. And exactly as we had in the harmonic oscillator, this is going to give us a ladder of states. Exactly as we did for the harmonic oscillator, we can solve for the ground state and all of the excited states, all of the different ladder of states by using these commutation relations. Okay, and at that, we are out of time. Questions and comments for me? Okay, I will be around in my office hours after this. If you guys have something that you'd like to discuss, I'd very much like to hear from you guys how things are going. Are you on track? If there's outstanding homeworks or anything that you owe me, get them to me as soon as possible. I will grade everything up until the last possible minute. All right. Thank you guys for your patience. Have a nice day.
Thank you.
Thank you.